Welcome to the video on the physics of music. In this video I'm going to talk about how do instruments make their sound, why does this sound nice, but this does not, and why is it that a D on the piano sounds different from a D on the violin. Or a D on the trombone. Actually, I don't know how to play the trombone, so that wasn't a D, that was some other note.
Let's think about it in more detail then. How do instruments make their sound? So the first thing I want to talk about are string instruments, right? So violins, violas, cellos, but also guitars and also the piano, right? They all have strings that vibrate. The different methods of getting them to vibrate. Do you have a bow that you move across it? Do you just pluck them? Do you hit them with little hammers, like in a piano? So, you've got a string of certain length, and we know what strings do. They form standing waves, right? So this would be the fundamental one I've depicted here. It's fixed on both ends. And the string has a certain tension and a mass density, and those together determine the speed, as we understand. And the length of it will determine what wavelengths form standing waves. So if the speed and the wavelengths are allowed to form standing waves, those determine the frequency. And frequency, of course, that is the pitch that we hear. Right? So each key, each note corresponds to a particular single frequency. The higher the frequency, the higher the sound we hear. Now you might ask, okay, fair enough, I understand standing waves and I understand that they vibrate and they bump into the air molecules nearby, and that's how the sound wave eventually reaches my ear. But how do they know to vibrate at that frequency in the first place? Right? Because when I say I pluck a guitar string, I don't pluck it with some frequency. Like I don't know how to do that. Or when I run my bow across a string on a violin, I'm not doing anything different depending on the note I'm trying to play, right? I change the note I'm playing by changing the length, by holding down my finger somewhere that sort of cuts off part of the string from the vibration. So how does the string know to vibrate at the right frequency? Right. So it's a little bit more subtle. So let's say I pluck. Let's take the example of plucking your string. Right? So you play guitar, or on the violin you play pizzicato, and you just pluck it. So what you're really doing in that case is you have your string and then having this shape here, and you store it over here, right? So you put my flat string, you create this sort of shape maybe, right? And here you're holding it right here. So that's the shape of the string, maybe it's a little bit curved, and then you let go. Where in this shape here are the right frequencies? Well, it's not a sine wave, it's some other shape, but any shape that's not a sine wave can be thought of or is physically identical to a large number of sine waves added up. Let me show this to you. Let's imagine the following. Let's imagine I want to build a sort of triangular wave shape, right? Like if I pluck a guitar string or a harp maybe, I create this sort of triangular shape. And I'm going to build my triangle between 0 and 0.5. Right? So I want a triangle sort of goes up and goes back down, sort of representing the shape of the string as you're just in the middle of plucking it. Now I could try this. Right? This is part of a sine function, but that is not the right shape. It has the right zeros here and here. Or it has the right wavelength, I suppose. But it's a curve, a sine curve. It's not triangular, right? And it's only one frequency. So what I can then do is I can add other sine waves. Now, how do I find the right ones to add? That is the theory of Fourier Analysis. And it's called Fourier Decomposition, to turn any function into a sum of sine and cosine waves. going to the theory is not what we're going to do here. We're just going to understand the concept. So here's my claim. To get a triangular function, I'm going to take this function up here and I'm going to add this one to it. So this is another function. It's minus 1/9 times the 3 times that frequency I had up here. Here the frequency essentially was 1. Right? 2 pi f is 1. Here my frequency is 3. So I'm going to add this here, which looks like this. Again, it's the right 0 points here and here. Oops, what did I do? And of course, I imagine my string ends here. It doesn't keep going, but the math function, of course, keeps going. So I'm going to add those two together. Then I'm going to add the next one, this one here. Now they're becoming very small because I'm having these factors in front. Now, how do I know to put them there? Well, that is that Fourier analysis I talked about that you're going to learn in a more advanced math course. Like, how do I determine the right form of those sine functions? My claim is, if I keep going in this particular pattern, right, instead of 1 over, I guess, 1 squared, 1 over 3 squared, 5 squared, 7 squared, and 3, 5, 7 in here, and I alternate plus and minuses, then I'm going to get a triangular function. So I'm going to show this to you down here. So this is a general expression, right? For each one of those, like this thing here, you plug in n equals 1, you get this one here. You plug in n equals 2 into this thing here, you get the second one. N equals 3, you get the third one, and so on, right? So you can, actually, n equals 0 gives you the first one, n equals 1 gives you this one, n equals 2, just n, right? Gives you this one, and so on. You can check that that's true. Just plug n equals 3 in here, you get, 6 plus 1, minus 1 to the 3, because that's this part here, and then sine times 2 pi, and what's this? 7, right? So this function here corresponds to n equals 3. Now I'm going to add them. And we're going to build up our triangle function like that. So initially, I'm just going to sum from 0 to 0. That's just the first term, right? It's just one term. The sum's so silly. Now I'm going to add the second term. So I'm going to 1. Clearly not a triangle function. It changed its shape a bit. It looks a bit better, maybe even. Like more like I might hold it here and let go. Let's go to 2. Right, so now I've got the first 3 terms added together. Let's add the next one. It's looking more and more triangular. Now I've got all the terms that I've written out here now added together. I've just written in the sum notation. We go add the next one. That would be with 1 over 9 squared and sine 9 times 2 pi x. It looks like it's getting better and better. It almost looks pretty straight here, right? If I zoom in, I can probably see a teensy bit of a not quite straightness. Actually really hard to do. It's already extremely good approximation. But then if I go to say 20, right, I have 20 or 21 terms starting at 0. I mean, this is almost a perfect triangle. Little bit of a curve still up here that's visible, but again, you'd be holding it there. So what's the point here? The point is holding it as a triangle, like plucking it by holding it here. You're really creating, by letting go then, you're creating a bunch of sine waves. We know how each sine wave acts on a string, right? The wave equation tells us that. Like this wave shape is a sum of lots of sine waves. So the sine functions, the technical term is they form a basis. And any other function can be expressed in terms of those, and that's useful because we understand what sine functions do. So when I pluck my string, what I'm doing by creating this shape is I'm creating all kinds of different frequencies at the same time. So why don't I hear all of them? Well, because only specific frequencies correspond to standing waves. Right? So I'm creating all kinds of frequencies at once, and most of them, they sort of bounce off the ends and they die down. Right? They're not constructively interfering with themselves. Whereas the specific frequencies that correspond to the standing waves, as determined by the wavelength and the wave speed, they will build up. Right? As the wave bounces back and forth between the two ends, they form standing waves of significant amplitude. So those are the vibrations that actually are visible on the string, but also correspond to the ones again then carried off through the air by the actual sound waves. Now, if you were to say, move your bow across the string, rather than plucking it, you don't get this same shape, you get a different shape, and instead of doing this once, you do it continuously, you're pulling on a single point. So you're kind of always like raising a little bit, making these tiny triangles continuously to add to the string. It's going to sound different. Another thing, you might have a triangle that's not, central. Like if you plug a guitar, you don't normally plug it right in the middle of the string. You plug it, closer to one end than the other, so that the shape of a triangle would look different, and you get a different decomposition into sine waves, but you still get lots of different frequencies. And we'll come back to that idea later when we talk about why different instruments sound different even when they play the same note. Alright, so we talked about string instruments. How about wind instruments? There are generally two groups. There's woodwind, like flutes and clarinets and oboes, and there is brass, trumpets, trombones, tubas, horns, all those kind of instruments. And you got a choice here. You could have an open tube, and that's mostly the woodwind, like for flute, for example. Or you could have a closed on one end and open on the other end. Right? It'd be brass, for example, a trumpet. You'd have your mouth on this side that closes the tube and it's open on the other end. But the logic of how certain notes get formed is the same, right? The speed of sound in this case, it's the relevant speed because it's the sound waves that form standing waves inside the tube. But then the length of the tube is going to determine what wavelengths are allowed to form standing waves. And those two together, again, determine the frequency. And remember from above, frequency is the pitch that you hear. Alright, so standing waves, we understand standing waves. Okay, but how does the sound get produced here? What's the sort of equivalent thing to plucking the string? Well, in the case of say a brass instrument, like say a trombone, right? You'd be blowing into this air. Now you don't just blow into it like, air. You're vibrating your lips in a certain way. That vibration alone does not produce the note. It produces all sorts of notes, much like plucking the string did. But then the length of the tube, combined with the speed of the sound, picks the right frequencies that start forming standing waves. And all the other frequencies that were included in this buzz that you made with your lips, they just die down and they don't form any form of standing waves. So it's kind of the same principle. You produce all sorts of frequencies, in this case with your mouth, but then only certain frequencies get picked, and those ones that get picked, well, that's determined by the length of the tube, which determines the wavelengths that form standing waves. In the case of woodwind, it works a little bit different. Like you might have a reed, for example, if you play the oboe, say. But also if you look at like with a brass instrument, like a trombone, you can very visibly see how somebody is lengthening or shortening the tube. But with a trumpet, you can, by pushing those buttons, you lengthen or shorten the tube through which the air travels. And of course an organ also fits into the category, and they just have fixed length tube, just pick the right one to blow air through by some mechanism. With something like a flute, you've got lots of holes in it, right? And what those do, well, they determine essentially how standing waves form inside the tube. So if you open the tube up in different places, then really the tube sort of ends here and here if there are holes in there. So by having different combinations of holes open and closed, you create a bunch of little tubes on the inside that form different standing waves. Or really that determine where notes and antinotes can form inside a tube. That determines the allowed wavelengths that form standing waves. That determines, together the speed of sound, the frequency. But again, by blowing into it, you create vibration, like the reed, right, that vibrates. It vibrates at all frequencies. It's not a nice sine wave. You just listen to a reed. It's this funny sort of messy sound, but then the tube picks the right ones that resonate. It's all about standing waves. Now, what about the human voice? The human voice, again, is sort of like this, right? It's inside your mouth and goes down to your throat, but then you've got your vocal cords that cause vibration. But then you can change the shape of your mouth to create different sounds, corresponds to allowing different modes on the of standing waves to form. We'll come back to that later on. Maybe you'll get me to sing. We'll see. All right. Now, what about say a drum? Now, a drum doesn't have a string. It doesn't have a length. It has a a surface. How do those work? Let me show you. All right. Let me talk about drums using the ultimate teaching tool, Wikipedia. So the article I called up is the vibrations of a circular membrane, because drums, they tend to be circular. So essentially you can do something on a surface with tension that's similar to what we did to a string with tension. You kind of just write down a wave equation for it. Now the wave equation is going to be more dimensional because it's a two-dimensional surface rather than a one-dimensional string. And it's going to look like this. So it looks very similar to our wave equation, except there's two sort of derivative parts, where in the normal wave equation there's just this first part here. Now we also have the second part in the other direction. And the c squared, that's really just a constant that depends on the properties of your surface, your membrane. Let's not worry about the math too much. You solve this. It gets kind of complicated. The two-dimensional stuff, you go through a bunch of multivariable calculus essentially to figure out what functions can form on the surface. You solve it. Here's the math. By all means, go through it. You might do that example anyway in a more advanced, say, math methods course if you're a physics major, for example, or in one of your math courses on multivariable differential equations, partial differential equations. If not, doesn't matter, right? Here's the math. Now, what does it look like? Here, like this. So, if you look at those shapes here, they are our standing waves, right? So they're two-dimensional standing waves. So far, we only had one-dimensional ones, in a long, thin tube on a string. But we can have standing waves in also harmonics, as they're usually called in that context, on a say two-dimensional surface, and they look like this. You can see the same patterns here. So this is your fundamental, it goes up, down. Right? It looks like the fundamental of a string that goes up, down. And this would be the next one. It sort of goes up, down like this, and then it goes up, down, up, and it gets flips back and forth. So these ones almost look like the string ones, except sort of in a circular way. But in addition to that, you get these additional modes where it's not symmetrical about the center. Right, and then so you have to label them with like two numbers, 0, 1, 0, 2, 1, 1, 2, 1. And here now they go in, say this one here, it sort of goes as up, up, like those two left, right go together, in front and the back they go together, and they oscillate like that. And then you combine this motion with this motion, you get those kinds of shapes here. It's a lot more mathematically complicated than the string, which are just simple sine waves of different frequencies. But the idea is the same, right? The math is harder, but the idea is the same. So when you hit a drum, again, you're not consciously choosing one of those modes. You can't do that. You hit it, and the deformation of the membrane can be expressed as a sum of all of those and more, different amplitudes, and then only the ones that form standing waves, like have the right size, because your drum membrane is fixed on the rim. That's kind of your boundary condition, right, which is fixed. And only the right frequencies that correspond to one of those modes, those form standing waves. Now, a drum, it has a certain pitch, definitely. Right? It can be it's sort of harder to play a melody on a drum. It's not to say impossible. Because you can't just shorten the string or decrease the radius of your drum on the fly as you're playing. If you could do that, you could actually play a tune on a drum. But it also comes down to standing waves. Okay, so let's summarize. How do instruments make sound at a particular pitch? So plucking, bowing, hitting, buzzing, blowing, whatever you do to the instrument, right, and it varies, that creates vibrations, but not at a particular frequency. It creates vibrations at all frequencies of the string, of the air in your air column, say in an organ pipe or in your trombone. But these vibrations at a large number of frequencies together, right, we could determine what those frequencies are based on using what's called Fourier Analysis, and spelled like that if you want to look it up. So the triangular shape of the string as you pluck a guitar string, right, it is really, or it can be thought of, it can be re-expressed as a sum of sine waves, and they each do their own thing, right? They each act like the other sine waves weren't there. Why? That is essentially mathematically, it follows from the linearity of the wave equation. Again, thinking about it in more detail is something you might do in a more advanced course. So that happens, then, right, the length of your string or tube or whatever else, right, that determines which of all those frequencies form standing waves. Right, so not all of them, you got a whole bunch of frequencies, but only some of them form standing waves. And those then cause the string, say, to oscillate at significant amplitude. That bumps into the air molecules nearby, and so you get essentially a pressure wave that gets carried through the air, right? Because the string physically hits the nearby air molecules. And then it reaches your ear, and you hear the sound at a particular pitch. It reaches the eardrum that vibrates. We could take it further, but it's not the subject of this lecture to give you the physiological side of hearing, right? So now we understand how musical instruments create sound at a particular pitch. So we want to ultimately also answer, well, why do different instruments sound so different from each other even when they play the same note? But before we go there, let's understand how frequency relates to pitch in more detail, and how different frequencies, say, work together to form musical chords, and what the particular frequency relations are of the types of chords you might actually meet in music. Let me take you to the piano.
Okay, so let's see how chords and music and melody is built from a physics perspective. Now, the simplest thing you can do is you just have some kind of melody, some sequence of notes. What makes a good one? I can't really answer that. But maybe you have something like this. And so on and so forth, right? Now, that was just a single pitch that moves from one note to the next. Now, it's interesting that if you track music through history, it's really a continuous progression of adding more complexity to the types of frequencies that go together. So let me explain what I mean by that. So the first thing you might do, maybe you're some Neolithic, or Paleolithic, human being, and you sit around the fire and you sing songs. And then you've got, for example, men and women singing together, and the female voice tends to be about an octave higher than the male voice. And so if you sing together, it might sound something like this. So we'd say music is the same note but an octave lower, but it's clearly a different frequency. Now if you do a frequency measurement of what it means to go up an octave, from say this A here to the next A here, the frequency doubles. And if we go for the next frequency, it doubles again. If I go from this one to this one, to 2 octaves, it quadruples. So it grows exponentially, right? Every time I go up the same distance on the piano, up the same amount of pitch, the ratio increases by the same amount of the frequencies. So this would be 220 Hz, 440 Hz, 880 Hz, so on. So simple 2-to-1 ratio. Right, the next thing you might do is you might go somewhere in between. So you might pick, well, the simplest one would be 1.5, right, a 3/2 ratio. Musically, that gives you a fifth, and it's essentially going up from the A to an E. And still, it sounds, fairly good. They go together pretty well. Right, and then I can maybe start again playing a tune. It becomes more interesting. It has a sort of medieval feeling to it, right? But that is the fifth, right? And then of course I can add back the full octave. So this is my bass note, 1.5 times the frequency, twice the frequency. Look at this. Now because I got the fifth, and this is the name of this sort of chord, I also have what's called a fourth. Namely, if I go from the upper note in my fifth, right, so the upper note here, to what was the octave of my original, here, that interval here is going from 1.5 to 2 of the original frequency, right? 1.5 times the original, this is my original, so 220 Hz, 330 Hz, 440 Hz. Going from 330 to 440 is a factor of 4/3, so 1.33, right? So if I have the 1.5, I also have the 4/3 because I already have the octave. So you can't have one without the other. And again, this also has a sort of medievalish sound to it. It's a bit of a vague, sense, but I think many people agree. And so, of course, you wouldn't necessarily compose music going constantly in fourth and fifth. It's considered bad practice for good reasons, but it's beside the point here, right? So we now have the fourth and the fifth. So we went from a factor of doubling, factor of 1.5, so 3/2, a factor of 4/3. So what's the next one that would make sense? Well, in that series, right? Maybe how about 5/4? 5/4. What does that do? So if I go from 440, whatever 5/4 of, 220, 5/4 of 220, what does that come to? I think that comes to, was it 275? Well, it takes me to here. I'll sound those two together. Again, that's a pretty nice sound. Maybe I should add the fifth, the 1.5, and the factor of 2, all of the original, like 1, 1.25, 1.5, 2. And that's in this case, an A major chord, right? If I had a different key, it'd be a G major chord or a D major chord or whatever. Now, by introducing the 5/4 ratio and also having the 3/2 ratio, I necessarily get the 6/5 ratio. Why is that? Well, this was 1, this is 1.25, from 1.25 to 1.5, and from here to here, 1.25 to 1.5, that's a factor of 6/5, right? 6/5 times 5/4 is 3/2, that gives it back the original. And this interval here, called a minor third. Again, the terms are not there for music. We don't worry too much about them. If you play music, they're probably familiar to you, but presumably not in terms of frequency ratios. So I start here. I go up to 1.25, 1.5, and so I've got the 5/5 and the 5/4 and the 6/5 ratio. If I go the other way around, if I go from 1 to 6/5, so 1.2, and then I multiply that afterwards by 5/4, so 5/4 times 1.2 is 1.5, or 3/2, so I end up in the same spot. but I go by a different note in between, and it sounds like this. So this is 1, 1.2, 1.5. So 1 is always my lowest note, whatever the frequency is. I don't care, I only care about the ratios. This is my lowest one corresponds to 1, 1.2, 1.5. If I add the full octave, the doubling of the frequency in the end, it sounds like this, which is an A minor chord. So it's the reverse. So do I go from 1 to 1.2 to 1.5, or do I go from 1 to 1.25 times 1.5? That is the difference between the major chord and the minor chord of a particular key. Now I can go beyond that. I mean, so what you have so far is really the sort of foundation of anything from the Renaissance onwards, right? But then things get more complex. So one thing I could do, for example, is let's say I want to add another 6/5 to the 1.5 that I have here, right? What's 6/5 added? So it's 1.5 times 6/5 is 1.8. So 1.8 of the original, not quite 2. Doesn't take me up the octave to 2. Takes me to if I start with A, takes me to G. Let's play those together. Still sounds good. It has a little bit more complexity to it, the chord, right? And it sort of feels like it wants to go somewhere. Where does it want to go? Well, how about here? Right? So for reasons that are probably in some way psychological, it sounds like this chord here had the 1, 1.25, 1.5, 1 to 8. It's not finished, it's not done, it wants to go somewhere else. So it wants to go here. Now, if instead I wanted to go from the 1.5, I want to not go times 6/5, but times 5/4. So it'd be, what is it, 1.875, right? It's called a dominant 7th. That is the, sorry, that was a dominant 7th. That's a major 7th. Again, this is music terminology, but that is very common, say, in, it starts getting us into the world of jazz, for example. Right? So we've traveled through the years, and we arrived in the 20th century. Of course, there were lots of other chords before that. It's not like people always stuck to chords, right? That you can build suspense by having clashing notes and having intentional discords that don't work together very well. And I'll give you an example of that in just a second. But in terms of the sort of the structure of chords that underlie how a piece of music tends to be built, it gets more and more complex really as we go through history, right? So we've now reached the jazz age, where I'm at something like this, the cocktail piano of the 20s, right? Might do something like this. Play some variation there, and we can go beyond that, right? And I think some composers in the late 19th century pride them, and early 20th century pride themselves on having the most complex chords you can possibly think of. And what sounds good, what doesn't, I don't think it can all be explained in terms of frequency ratios, but clearly those basic building blocks of a piece of music, right, that is based on those simple ratios from the 1 to 2, 1 to 1.5, 1 to 1.33, like 4/3, 1 to 1.25, like 5/4, and so on. Okay, so that's the basic. Let's just look at some examples of how that might appear in music. Let me play the opening 2 bars of Chopin's Nocturne in C# minor. Sounds very nice. What are the chords used here? Well, I wrote this handy chart to show you, right? So up here on the top part, I wrote the actual keys. The bass note that we start out in as our kind of go-to note that is the basics for everything that's going to happen next. Hard to put into words. That's the C sharp, the C sharp 3, which is 139 hertz. It's this note here. Everything is kind of built on that in that particular piece. Right? So these are just the notes. Again, if you read music, you recognize them. If not, but here are the ratios. So I always pick the bottom note. I called it 1, right? And then I build the chords on that. So the first one is 1, then 2.4. So kind of there's not much in between. 3, 4. So very simple ones. Right? That was this first chord. It sounds like this. Then the second one, it again is the same one here, and then it's 2, 3, 3.6. It's a very simple ratios again. Right? So that was this one. Now what happens then is that the note at the bottom actually changes. Right? It goes up by the 4/3 factor. And then if this is my new one for this new chord, then you get these ratios up here, and then you go back down to the original. There's always two types of ratios to consider. There's what ratios build the chord, right? Called sort of the vertical composition of your music, and then what ratio takes me from one note to the next. I call it the horizontal composition, because music is written, in vertical notes on top of each other. I mean, they're played at the same time, and then you go to the right. And then it takes me down here, times 4/5. This is sort of intermediate one. That takes me, then it ends at the 3/4 of the original. Right? So let me play this again. There's an example of music using those very simple ratios in some combination at the same time and going from one to the next to make, frankly, beautiful music. Alright, let's take another example from music, and again I'm going to use Chopin, where we are intentionally breaking those nice harmonious frequency ratios. Right? So here are the opening bars of the final movement of his B minor sonata. So what happened there? Let's look at this opening. This opening section is very simple. These are all F sharps, so there are 4 times the same note. On my convenient frequency chart, right? The bottom note is the F sharp. I didn't check what actually the frequency of an F sharp is. You could probably work it out, but doesn't matter. That's my 1. And then goes 1, 2, 4, 8. Right? These are octaves. Then it does the same thing an octave higher, 2, 4, 8, 16. So that is extremely simple. I mean, it's loud, it's fast, it's a lot of notes or a big range. It's fairly dramatic. Just by itself. 4, 8, 16, 32, then back down. So the first section up to here with those very simple doubling ratios was this. And then, so what we could have done is just repeat. Right? So it might have been still a very dramatic opening. What actually Chopin does is he adds another note. He adds, hope you can see this up here, this 5.33, but it's just 4/3 of this one here. Right? 4 times 4/3 is 5.33, and that would sound like this. It's already very dramatic, but that's not enough, right? What Chopin does instead is that he, like a madman, shifts those frequencies at the bottom from 1 to 2 to 1.06 and 2.12. Now what are those ratios? 1.06 is the ratio it takes you up a semitone, right? So it means the bottom two notes that octave apart, they both go up by a semitone. And so you end up with this. Right, that is clearly a discord to some extent, right? If those were closer together, it would sound like this. Shrillness to it. But it's used for dramatical effect, because then afterwards he goes on to essentially resolve it. Well, first is an intermediate one here. Actually, you can change it up a bit in the end. It's not the point. Right? The point here is that this semitone difference, this bizarre ratio of 1.06, is used for dramatic effect. Right? So, beautiful chords, nice frequency ratios, yes, but that alone doesn't make music. Right? Music needs to be dramatic. And that's just the opening. Alright. Just occurs to me there's another kind of chord or type of chord that's featured in music a lot, usually for some kind of suspense purpose, that is really interesting in terms of its frequency ratios. So far all our chords, they started with a single note, then had sensible multiples, like sensible fractions of the note, like 5/4, 3/2, right? It was never anything crazy, with fairly sensible ratios. Now, what if, instead of starting the bass note and going up by like 6/5 of that note, 3/2 of that note, what if I start on one note and then go up by a particular ratio and go up by the same ratio but from the second note? So I kind of go up by, say, 3/2, then 3/2 of that, and 3/2 of that, and so on. It corresponds to equal intervals on the piano. So if I stick with the simplest one would be the just going up octaves, right? Double, 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 right? It sounds like this. It's very simple. But what if I go up by, say, 1.5? So 1.5 is 1, 1.5, then 1.5 times 1.5, that's 2.25, then 1.5 of that is 3.375, I think. It'll sound something like this. Beyond that, it sounds more complex. I think it's a really nice chord. And what about other ratios? What about if I go up by 6/5? That's the minor third of this chord, right? From here to here. Before I then decided after the 6/5 I'm going to go by 5/4. That takes me to the 3/2 of the original. It was my minor chord. What if I stick to going up by 6/5? From here to here, here to here, here to here, and I get this. Which is a diminished 7th. That's again just musical terms. And it has uses, but it's definitely sort of suspenseful, right? It's not the ending of a piece, ever. It'll keep going from there. And what about if I go up in the 5/4 ratios, right? So that was this interval rather than the 6/5. If we go up in this way, something is again pretty intense. I think I call this the murder chord because every time there's a murder on TV, that's the kind of chord that is used, like in the music, for example. And of course, you can find other ratios too, like you go up. But all those chords seem to have this fairly intense feeling to them. Or how about making it a smaller ratio like this? Right? They're not outright crazy discords, but they sort of have you sit on the edge of your seat, waiting to see what happens next. Of course, the emotional response we have to music, that's a question I can't answer. Okay, so let's start with a single frequency and then listen to notes that are multiples of that frequency. So I'm going to pick the A1 note, which is right down here. It's my bass frequency. So I wrote this handy chart with the frequencies on it. So we're going to start with A1, and we're going to double it, and we're going to triple the original, then quadruple the original, and so on. Now initially it's going to take us up an octave, because we've doubled it, but from here to here it's only a factor of 1.5, so it only takes us up by a so-called fifth. And so the intervals on the piano are going to get smaller and smaller, because the ratio from one to the next is smaller and smaller, because it's all just multiples of the original. Right? Let's listen to what that sounds like. And it keeps going. The issue is, as the notes get higher, the actual frequencies I need to hit are somewhere between the notes. So after having gone all the way to here, I probably get, this would be the closest, but there just aren't enough notes on the piano. I need sort of in between notes to actually hit the precise frequencies. In fact, already here, at least those two, the C sharp, and this note here, and the G4, which is this one here, they're already a bit approximate. They're like off by 2 or so hertz of what the actual instrument plays. But it was the closest I could get to play you this overtone series on the piano. Okay, so here's a piece of music that actually makes use of this series, starting with one frequency and then building on multiples of that one frequency in order, like this overtone series. So this is the piece called Alte Sprach Zarathustra by Richard Strauss. Do you know it? Well, if you think you don't know it, chances are you might actually recognize it once you hear it. So this, you start with a very low C, like the lowest C that you can place it on a counter bassoon, as well as like double basses and so on. And then it builds on that with going up to the higher Cs and the G and the C, and it builds on that series of notes that I just played to you, starting with an A, while here we start with a C. So we listen to it. What you'll find though is that this first note is super quiet. You might have a hard time hearing it at all. I haven't found a good recording where it comes out very clearly. So it's really a sort of concert goer experience, I suppose. But once the actual tune starts here with the next C, the G, this going up the series, you'll definitely recognize it. So let's listen to it. Alright. You probably recognize it. We weren't able to hear the very low C. Maybe it just came through, but then going up in the series was used here for dramatic effect. So going up an octave doubles the frequency. What's the smallest step I can move up on? Maybe on my tone generator I could pick any tiny frequency, but what about my piano? What about, the notes that we use in Western music? So the smallest step you can go up is what's called a semitone in music. Again, that's just terminology. It just means you go up to the next key. So if I start here, I go to the black one up here from the C to what's called a C sharp, or depending on context, the D flat. It's called a chromatic scale in music, going up like that. So, but how big is that step in terms of frequency? Well, here's what I know. I know going from here to here, it's an octave that doubles it. Double, right? Now, how many steps is that? Well, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. 12 steps. Each one of them is a semitone, so that means going from one to the next, each time I multiply by the same factor, right? The frequency increased by the same factor. Now, what is that factor? So I've again written out a little note here to show this to you. This calculation, right? So this teaching in a nutshell. Frequency doubles, right? Every 12 steps. So we go from 220 hertz to 440 hertz. My example is for the A to A rather than C to C, but doesn't matter, right? I multiply by some value, let's call it R, every step of the way, right? So as I do it 12 times, I have 220 times R times R times R times R, and so on, 12 times. So at 220 times this, what's that factor? What's the semitone factor to the 12? That's 440. When you do the math, you want the 12th root of 2, and it comes out to be just under 1.06, 1.59 something, right? 1.06. So that is the smallest steps that I can take on the standard Western scale of music. Now, some modern music uses, sort of quarter tones and so on, and you slide between notes. There's also things you can do. We're not limited by this, but that's kind of the baseline. This 1.06 ratio. Now at this point you should be confused. You should be confused because yes, 1.06 to the 12 makes 2, taking from here to here. But hold on, didn't we say the fifth was 1.5? What's this? What are those steps? Let's go. How many steps is it from here to here? 1, 2, 3, 4, 5, 6, 7. Now, 1.06 to the 7 does not make 1.5. It gets you pretty close. You can get out a calculator and try it, right? It gets you pretty close, but it does not get you exactly to 1.5. Similarly, what about the fourth? This thing that takes us from here to here. So this is the sort of the thing that came with the fifth, because we also have octaves. Or I could go from here to here. Right, the fourth, again, very common, say in medieval music, but in all music, right? But this is kind of just don't sound very medieval. But what is the ratio here? It's meant to be 4/3, right? That's what we talked about. Well, let's work it out. So it's 1, 2, 3, 4, 5 steps. Right? The fifth was 7 steps. The fourth was 5 steps. What's 1.06 to the 5? Again, it's not exactly 4/3, so 1.33. Right? It's something just ever so slightly off. So what's the upshot here? The upshot is that all those frequency ratios we talked about are really just approximate. They're not exact. And you can tune an instrument differently, so you can do what's called equal temperament tuning, where you literally do the 1.06 factor. Or you can tune your instrument so that the 1/5 is exact, but then you have to tune it for a specific key to work in. Like I can't have this be exactly 1.5 and this be exactly 1.5 at the same time. It just won't work. Right? So do you do equal temperament tuning, in which case the ratio of 1.06 is exact, but the 1.5 and the 1.33 and the 1.25, they're not exact. Or do you make those exact, but you have to kind of pick a specific key to do that in? So it's a bit more complicated than that simple story of 1.5s and 4/3 and so on, right? But approximately that story gives you the right idea. And people fret over this day and night, maybe when they're professional musicians, I suppose. How is the instrument tuned? Can they maybe use it to some new avant-garde compositional effect? Who knows, right? I'm not an expert in these things. Maybe we can talk to an expert some other time.
All right. So now we understand chords, we understand frequency, how different frequencies sound together. and the upshot was nice ratio, seems to make very sort of pleasing sounds. So let's actually turn to the final big question, then why is it that different instruments sound different? Now, on the face of it, it seems a bit of a silly question, right? And a violin is a violin, a trombone is a trombone. But it's a bit strange that if you think a particular note is a particular frequency, particular sine wave, well, ultimately what arrives at our ears is just pressure waves. How do the pressure waves know? How do these sine waves know whether they were produced by a vibrating string or by a vibrating air column? So to figure that out, I have opened up in Audacity. There's a program you can get for free for sound analysis and manipulation and so on. I've opened up the recording of various things that various sounds you've heard so far. So here's the violin, right? So we're going to analyze that sound, and we're going to contrast it with the trombone. There you go. And we're going to contrast it with the violin when plucked. It sounds like this. So pretend I'm playing it like a guitar, playing pizzicato as it's called. And then of course finally my voice. I promise I'd sing for you in the end, right? Yes, that is me. I'm singing a D with two different vowels, right? An O and then an R. Why do they sound different? Kind of the same answer as why different instruments sound different. So let's start with the violin. So here's my violin, and I'm going to zoom in on that wave. Now, you can't really see it very well here, right? It's too far out. This up here is in seconds, so there are way too many oscillations. Let's zoom in. Now what you can see at this point, we stop here, is that, make this bigger, excellent. What you can see is that that wave is not a sine wave at all. Right, this is some kind of mountainscape here. Of course, if you look at the pattern carefully, you see that the pattern repeats. Like let's start at this peak here. It goes down, does some wobbles, so the bigger wobble, up, down, and then it goes back. And here it starts again, right? This peak is the same as this peak right here, and then again here. So the pattern repeats, but it's not a sine wave. Okay, so that's interesting, right? It's not a sine wave. What about other ones? Let's listen to. Let's go to the violin, but plucked. So here's. Maybe go zoom in a bit and go a bit to the left. That's a bit louder. So here's a plucked. The pattern looks very different. Bigger too. Right? It is different sort of. It's somewhat simpler than the previous one. And it's this high peak, then a little peak, then down deep valley, and it comes back up, and it repeats. Again, it's not a sine wave. So the wave shape looks different. What about the trombone? The trombone wasn't a D, so the frequency is different, but we weren't paying attention to that anyway. Let's have a look. So here we go. You can tell, again, very different. There's this high peak, and it goes down, and does this weird thing down there, and two little bumps here, and it goes back up and repeats. And it's very regular. It repeats every time. It's extraordinarily regular. But it's not a sine wave. It's a more complicated repeating pattern. Finally, let's look at my voice. Here we go. Let me make it bigger. Zoom in a bit. Oops. So where are we right now? So this should be the early one where I'm seeing the O sound here. Zoom in a bit more. It's actually a very simple one. It's almost a sine wave. It's a little extra bump right on the way up. And then I go to the right where it's changed the vowel I was singing. Here we go. It looks very different. So this would be the other letter. Let's check that it's true. Right, it was the R sound, and somewhere over here, to the left of it, that was the O sound, which actually turns out to have a simpler shape than the R sound. But you can clearly tell I was singing different things. You check the frequencies. Here's the time. I'm not going to do the math here. You check the frequency of this repetition. Right, you measure the period. You'll find it's the same, but the shape is different. So can we make this idea more precise? That different instruments, different qualities of sound, different timbres, that they create a different wave shape. Like, can we analyze it in more detail? Yes, we can. So here's what we're going to do. We're going to use our understanding of that any wave can be decomposed in a bunch of sine waves. So we're going to do this to our violin. So I'm going to select a section of what we just heard. Let me show it's kind of a uniform section here. It looks all fairly the same. Now, we could do this again by hand if we had a mathematical function, do this Fourier decomposition. I'm going to just let the computer do it for me. So here's what I'm going to do. I'm going to use, it's an inbuilt function here. Go to analyze and plot spectrum. Like, spectrum is another word for decompose this thing into its frequencies. So here's what we get. Let me make this a bit bigger. Let's take a moment to interpret this. So at the bottom you see the various hertz, right? And here you see a decibel value, and of course remember decibels corresponds to the loudness of it, the intensity of it, but remember it's on a log scale, right? So I think going up by a fixed number of decibels, right, means a certain fractional increase of intensity. So, and what you notice is there's a lot of, like, there's kind of sound at all frequencies, right? So what is this telling me? It's telling me, look, this signal that we saw is made up of a bunch of different sine waves, and this is telling me the amplitude of each sine wave for each frequency, right? So this one here, you see the spikes here, like these thin spikes. I tried to find a way to, like, enlarge this, but there hasn't been a good way to do this. So I'm going to just work with this picture here. Let's go to the first spike right here. Now it tells me right underneath that is a D4, right? It says in the line down here, if you pay attention to what it says down here, when I hover over this first spike, that is, yeah, missed it. Next to D4, right? 296 Hertz. And that's fairly high up here. Now then there's some messy stuff. Again, because it's on a log scale, this, it looks, it's like, you know, more than half the height of this, but actually a lot more quiet. So those sine waves at those intermediate frequencies, let's forget about those. Might just be background noise. So let's go to the next spike. Next spike is right here, right, which is, as you can see in the line below, D5, so the next D up, so that's interesting, 586, which is just twice 296, roughly. So it looks like this note that I played, like the D came out as a spike, right? I played a D, remember I played the D4, so that's what it's showing me here. That's my first spike, that's the note that I think I played. But also sounding is the D, the next one up, double the frequency. Does that make sense? Well, yes, it does, because D, the D4, might be the fundamental that gets created on the string, but of course the overtones, the higher harmonics of standing waves, they can also sound. So this here, the second spike, right, that you see right here where my cursor is, it's a bit hard to show you, that is the next D up. Now it's hard, if I miss a little bit with my cursor, I end up on the C sharp or something, right? I keep doing that. It's rather fiddly. Now what's the next spike? There's a little spike down here. That's the A, the A5. Okay, that's interesting. Remember A is a fifth above this D. So that means this is ratio 1. This is like frequency 296, twice to 96, 3 times to 96. There's some rounding, of course. The next one, it's another D. The next spike, the fourth spike, is another D. So it goes up in this series of constant frequency steps, right? This is the bass, 296, twice 96, 3 times 96, 4 times 96, and so on. They're equally spaced, those spikes. And so those correspond to all the different modes of standing waves. You can tell even like the high ones down here, these standing wave modes here, again it's an A. Right on A sharp it says, well, maybe a little bit off. Maybe I was the teensiest bit out of tune with my D. Wouldn't be surprising. Here, this one, A8 it says below, 6,931 hertz. Right, but it stands out from all the background noise that's going on. So all those are all the different overtones, and they all seem to sound, the early ones, the low ones, at the largest amplitudes though. Right, so those are the most audible. Let's look at a different sound. So let's go with the plucked violin now, right? This was this. Apparently I can't play it now. Okay, what happens? Can I play this? No, apparently not letting me play it. Alright, doesn't matter. So I'm going to select a chunk of this here, and I'm going to do the analysis for this one. Plot spectrum. Oops, that's a different one. It's not what I want. This is the one that I want. Now this looks very different, right? You can tell though, again, here, this is my D. The first spike is my D, and then the next one down is my next D. This should be my A. Yes, it is. And then the next spike is my D again. Yes, it is. So always check what it says here. So these spikes again correspond to the standing waves that get formed on the string, right? Starting with the bass frequency, D, hard to hit my cursor, D, the next D up, 1 octave up, then the fifth up, that's 3 times the original frequency, 4 times, 5 times, right? Exactly those standing waves allowed to form. But the amplitude of those individual spikes is different from the ones that we saw here, right? Not only is the whole thing louder or more quiet, you can tell this one goes like up, then down, and back up. Whereas this one here, it goes here and it goes down, up, and then it sort of goes down and down further. So the pattern of overtones is different. It has the same overtones, but they sound at different amplitudes. And that creates this different shape of wave, and ultimately the different sound that we hear. Let's go to the trombone. So the trombone looked like this, right? This sort of funny double bump, then tall spike shape. Let me zoom out a bit. Nice section here already selected for me. And let's analyze that one. I'm going to plot the spectrum, and here you go, right? Let's check this out. What's my first spike? It's a B, right? So I told you I can't play the trombone, so I didn't know what note I was playing. I had a B apparently. This is a B. Oops, there's a B. Then the next one up is an A. That's interesting. I think I went a bit off there. And then here an E. So you get the same sort of overtone series, right? The multiples of the original frequency. Oh, hold on, it's an A. Apparently an A. The first spike, then another A, then a. This is a bit off. Interesting. E here. So I think I was a little bit above the A, right? But if you look at the frequencies, they're equally spaced. They go up in equal steps. And again, you get a sort of pattern that's, in this case, the second one is fairly high, but it's sort of this descending gradually. Some higher ones, you're not going to hear those very much. Like if you were to cut those off, like above 5,000, you cut them off, you wouldn't be able to tell. And when you have a low quality versus a high quality sound file, for example, like one way to save space in terms of the file size is to cut off those higher frequencies from your recording, because they're often so quiet we can't hear them anyway. The change that makes the sound quality is very small, right? There's a lot of storage space. You don't need to store the information in these ones. And then you get the sound of a trombone. And if you listen very carefully, you might hear the difference if those ones were missing, right? So that's a way to compress sound files. Or if you're asking, what quality of sound file do you want? What's the difference? Well, this is part of it, right? Are we cutting off some higher frequencies? All right. So this is a trombone. Now let's look at the voice. In the voice, we had 2 of them, right? I was singing 2 different notes. So, oops, what happened here? Find it again. So over here, Right, so over here is the O, over here is the R. Let's have a look. And we already looked at what those shapes look like. So let's analyze those. Oops. Good to see. Here we go. Now this is a very clean spectrum. What I mean by that is there aren't many overtones, right? And you could tell that the shape of it was very simple. So here's the D. I hit it. D4, right? The same note as on the violin. The next one is the sort of bit of a broader spike, D5. And then it's the A, and then there isn't much beyond that. So it's a very simple sound. It's almost a pure tone. It only has really two overtones that you heard that made up that quality of that sound. That's this part. Now let's do the same thing over here where we're singing the R sound. So let me plot that spectrum for you. It looks different, right? When we looked at the shape was different, but here I've got essentially three tall spikes. It's like the third one's almost taller. It is taller than the other two. Right, this was the D. Where's the D? There you go, D. And the next D. Did I hit it? I don't know, maybe it was a little bit flat at that point. A, and then the next one, the next D is coming through the next, should be an F sharp. There-ish. Yeah, it must have been a little bit flat in my singing at that point. Maybe you could hear it if you got perfect pitch. Maybe you couldn't. But well, the sound analyzer certainly can hear it. But that pattern here, right, has essentially 5 spikes. The first 3 very large, the next 2 smaller, whereas the O sound pattern only had the first 3. And the way I do that is by changing, like what I do physiologically speaking, is I change the shape of my mouth, right? Essentially of that pipe, allowing different notes and antinodes to form in different places, because it's not a simple pipe that the air forms standing waves in. It's a pipe with bumps, right? And nooks and crannies. And by changing what those nooks and crannies and bumps are, I can change what standing waves come, what modes come through. It's a little bit analogous to woodwind. In fact, if you listen to woodwind like a clarinet or a flute, it also tends to have a sort of cleaner spectrum than, say, the trombone or the strings, which have many more higher modes excited, like many more spikes on our spectrum. All right, so now you know, right? And now you know the difference between a violin and a trombone. They play the same note, but there are different overtones that come out to different degrees with different amplitudes, and therefore the actual wave shape, when we zoom in, it's not a sine wave, it's a sine wave plus overtones added together, making a more complicated but nonetheless repeating pattern. Now, if you're into, say, electronic music or synthesizers, right, then what you might do is you might manually, on your program, on your device, set what overtones come through how much. So you can create new instruments on a computer, like in electronic music, by creating your own spectrum by choice, right? So in our case here, we had those spikes and then the lower spikes. Well, if I could manually change the size of each spike, right, I'd be making electronic music. I could try to reproduce a violin or a trombone, or I could, create new instruments from scratch. That is electronic music for you. All right, then we're almost at the end now. Right, we're back at the piano. Now, here's a simple experiment you can do if you have a piano or access to a piano. And the experiment is there to show explicitly that indeed, if I hit a note, I get some of those overtones as well. Right, so here's what we're going to do. I'm going to take a note, say this A here. And then I know that its first overtone, right, this is 220 Hertz. Its first overtone is going to be 440 Hertz. Right, that would be the 2 antinode vibration, and this being the fundamental. So that corresponds to the fundamental of this note here, up the octave. So what I'm going to do is I'm going to hold down this key without,
gently, so it doesn't make a noise. What does that do? Essentially, inside the piano, it releases those dampening cloth bits that are on the strings. It takes them off, and if I hit it hard, the hammer hits at the same time. That's how I get a sound. But if I just do it gently, the string is now free to vibrate, but I haven't hit it. So I'm going to now sound a lower note, and I let its overtone get this string over here swinging. Now, what we should hear is I hit this once, and we should hear a quiet hum from the upper note. It's going to be fairly quiet. I don't know how well it shows up on the recording, if at all. So that's really something you should try at home if you have a piano. Let's go for it. Right? Try it again. This one, I push it very quietly, no sound. I push this one just briefly and let go. Right by itself, stops. I hold this one down. I can hear this ring from the upper note. Let's go higher. The next overtone of this one here is not the octave, there's this one in between. Like it's 3 times this one. Remember, we understand chords and their frequency ratios. I'm going to hold all of those, and then maybe also the next one up. So 2 times, 3 times, and 4 times the original frequency. I'll hold all of those down. Alright. No sound. Now when I hit this one, we should hear all of those up here. Alright. Not sure if you heard very much at all. Let's go up a bit more. Again, this is something that works way better if you try it at home. Do it carefully. Bunch of notes up here. They should all be overtones of that A down here. Not sure why it came out in the recording. Right? So if you can, do this at home. It's living proof that for any note, the overtones get excited. And that's also something you can use to tune a piano. You could also try, and you need to listen very carefully to make it out, is I could use the fact that even if one note here is not an overtone of the A, they might have joint overtones. So say this one here, the E, it's 1.5 times this. So the one that's 3 times this one, the E up here, is an overtone of both. So technically, if I hit this one, hold this one down, I can't hear this one, like the fundamental, because that's not an overtone of the A, but I should be able to hear the first overtone of this, which is the same as the second overtone of this. Right. Again, I doubt it's going to come out on the recording. You might as well give it a go. Also some background noise in the piano. In fact, some of the upper keys would always ring because they're not dampened in the same way. Again, you can just open a piano, look inside, look at the mechanism. But if you can't, try this at home. Or, friend's house, go to piano, just sit down and try it. You've reached the secret section at the end of the movie. Alright, so remember the thing I played to you? Those opening bars of the C-sharp minor nocturne that demonstrate those nice chord progressions with very simple ratios. Well, I've decided we're going to jazz it up a little bit. I'm not very good at playing jazz, but we're just going to work with some frequency ratios. We're going to add some in to jazz this thing up. So here's what I was thinking. Right? Here's our chart, and I'm going to add some ratios. And if you look at those, what I've decided to do is I'm going to pick essentially ratios of 1 that are not sort of the same type of ratios that are already there, but they're not like crazy, like 1.8, 4.5, so this is like twice 0.9 and 5 times 0.9, so they're kind of a similar vein, right? And here I've got 1.33 and then twice that, 2.66, and then I'm just going to put something on the bottom, a 0.5, and then over here I'm going to add a 1.5 and a 1.5 squared, so a little bit of this exponential stuff, right? You take the same factor and you multiply it by it again. I'll leave this one unchanged. It was already kind of an interesting one. And then we're going to add a 1.8 and a 3.6 to the final chord. Right? Let's see how that sounds. So, of course, I had to pick ratios that exist on the piano. Let's see what happens. Just adds a little bit complexity with the sort of smooth, jazzy chords to it. Maybe change the rhythm too. Well, you're not that lucky.